Part D.3, Introduction to Selection Problem. The second part of Part D, we want to work on a new problem. Actually, it's not a new problem. We did one special case in Module 1, but for the general case, it is new. So let us look at the general case first. Our problem number 13, the general selection problem. Given an array and a positive integer k. The question, how to find the kth smallest element? Kth smallest element. We did a special case, that is the first smallest element, right? The minimum value problem for an array. We did that in our module 1, and we found an optimal solution. But here, for arbitrary given k, that number, we need to find the kth smallest element with an efficient algorithm. The goal, efficient algorithm. We do not require optimal. Here you can see we do not require optimal. Why? Because it is too difficult to get optimal solution. Nobody can do that. That optimal solution for this general case, currently, nobody in the world can do this. Nobody can do this. All right. So, but we can accept a relatively good solution. All right. So let's continue our discussion. This k has another terminology for it. It is called kth order statistic. So its official name, kth order statistic. But in our discussion, we like to use a simpler, shorter term for this k. So we call it rank equals k. If k is 1, we call it rank equals 1. This element has rank 1. The first smallest element, and so on. 1, 2, 3, 4, 5, and so on. All right, so now let us do the analysis. In this analysis, I want to give you the general idea to solve this problem. Just idea. So in this video, short video, we only discuss the general idea. We will not work on the implementation details. Later, I may use other videos somewhere else. I try to describe the implementation details. I just describe, give you more information about the implementation details, but I like to skip, a lot of tedious manipulation. Some tedious manipulation. I just give you, we do this way, but some tedious details I like to skip. All right, next, the idea. First, we notice the data is unordered. For a question like this, data is unordered. Otherwise, it's trivial, right? If data is ordered, it is trivial. So we assume the data is unordered. Second, the question, should we sort the array first? Well, it is quite natural. Some people may like to sort the whole array first. Then it is very easy to find any element with given rank k. All right? But here I like to tell you, if you do this way, the efficiency is not very good. Why? Because when you do the sorting, you need to pay the cost, the big theta of n log n. Why n log n? We haven't learned that, right? Why n log n? In next module, we will learn it. Next module, yeah. Next module, we will learn two algorithms that can give us this kind of efficiency. All right, so here we just assume, yeah, there is such algorithm available. Yeah, all right. Number 3, how do we divide the problem? Divide and conquer, yeah. So we use the divide and conquer approach. And here, let me give you the idea on this divide and conquer approach. Now, first, we divide the problem into 2 subproblems. How? Yeah, so that kind of details we will fix in the implementation part. All right, so then drop one of the subproblems. Now, based on the comparison, now we need to do one comparison after we divide in 2 parts using some special way. All right, yeah. Then we do one comparison. That one comparison can help us drop one of the 2 subproblems. So after one comparison, we can drop. Yeah, because you get information from that one comparison. If you want to get better understanding, you can use our binary search, right? Binary search, we divide the original array into 2 almost equal size subarrays. Then after one comparison with the median, we drop one of the subarrays. So you can use that example to help you understand this idea better. Yeah. Next, convert the original problem to one of the subproblem. Yeah. After you drop, now you need to work on the subproblem. But when you work on a subproblem, you may need to do some work to make it look like the original problem. What do you mean that? Here, this step you may not be able to understand, but here, let me point one thing out. You can understand why we need to do this conversion step. Yeah. Here, you may need to do this kind of conversion. Yeah. For example, for the original problem, we need to find the kth order statistic, right? Kth order statistic. But after you drop one of the subarrays, do you still find the kth order statistic? Maybe not, right? Yeah, maybe and maybe not. Yeah, so you may need to convert it to rth order statistic. Rth order static, but this is one of the cases. Yeah, maybe case you need to do the conversion. Maybe not. Another situation, another case, maybe not. So what is that maybe case? Another is maybe not case. Think about that. All right. This is the original problem. All right. Yeah. You divide it into 2 subarrays. This time we cannot get even division. We cannot. Okay. Yeah. Later you will see it is very hard. So we do not expect equal division. Yeah. All right. Then when you drop, think about that. If you drop the left subarray and your kth order statistic is here, now you need to recalculate the order statistic. Here, that's the rth order statistic. That's what I mean, maybe. Yeah. But what is maybe not? If you drop the right subarray, then you don't need to change, right? You keep the left subarray, so you still work on the kth order statistic. So that is what I mean here. Yeah, that is this step. Yeah. All right. So after you understand, all these basic steps, later we can move to implementation details. Yeah. But before that, here I want to talk about a little bit about the elimination idea. Yeah. We know in this part we use elimination idea a lot. Yeah. And here I want to point out one special property. We can use it to improve our efficiency of the algorithm. Yeah. So what's that? Yeah. When you do the elimination, you can consider two possible cases for the elimination. Yeah. The first one, eliminate certain number of elements from the left end. That is one possibility. The second possibility, eliminate from the right end. Yeah. You can also consider do elimination from the right end, two ends elimination. Okay, yeah. So if we use the diagram, yeah. So sometimes you consider do elimination from the left end. Sometimes you do the elimination from the right end. Because in this way, you can explore more useful information. If you have more useful information, you can improve your efficiency of your algorithm. Yeah. Here, when I talk property like this, it is very abstract, right? Very abstract. It is very hard to imagine. How do we use this property? Yeah. Don't worry, later I will have several examples. So I will show you how to use this property to get the best solution possible. All right? Yeah. Then another thing, yeah, before I finish this video, another thing, yeah. When you use this property, there is one thing you may need to do. Yeah, simple thing, yeah. That is the kth smallest element equals x largest element. There is a relationship between k and x, right? Yeah. There is a relationship between k and x. When we look at the kth smallest element, we count from the left end. But can we count the same element from the right end? From the largest side, there is a number, right? Yeah. So that number, to get the relationship, there is a simple way. Just look at when k equals 1, the first smallest element. If k equals 1, the first smallest element equals what largest element? Nth, right? Is it nth? Because n elements. Nth, the last. The last largest element, nth smallest element. Yeah. So you can see here, 1 plus n equals n plus 1, right? So that is k plus r equals n plus 1. So we have this relationship between k and r. Yeah. 2, when k equals 2, r equals n minus 1, right? 2 plus n minus 1 equals n plus 1. When k equals 3, r equals n minus 2, and so on. Yeah. So this is probably pretty simple, yeah. But sometimes you may need to use it to apply the property we discussed here. Yeah. All right, so let me finish our discussion of D.3 right here.